Okay, hello everyone. It's great to have Annie Raymond today as our speaker. She is from University of Massachusetts, and she'll talk on graph density inequalities, sums of squares, and tropicalization. As usual, maybe this is your first time to this seminar. You are welcome to write your questions in the chat box, or you can also just unmute yourself and ask Annie the question if Annie is okay with that. Is that fine with you?
Definitely.
Yeah. And then also at the end, we will have lots of time for question and answers. Usually the talk is around 50 to 55 minutes, and then we have some time at the end for Q&A, and then also at the end we just have some informal discussion which is unrecorded. Yeah, I think that's all. Let me just, yeah. Annie, you can start.
All right. Well, thank you all for being here. Thanks to the organizers for the invitation. So yeah, I'd like to talk to you a little bit about some recent work about how to use sums of squares and tropicalizations to understand inequalities involving graph density inequalities. And so this is joint work with Greg Blekherman at Georgia Tech, Mohit Singh also at Georgia Tech, and Rekha Thomas at the University of Washington. So I'm going to start by making you all do some work just to make sure that we're all on the same page. So I want you to draw a graph on 7 vertices, your favorite graph on 7 vertices, or a random graph on 7 vertices, whatever you want. And I want you to count the number of edges there are in it and the number of triangles. So for example, I'm drawing this graph. It has 9 edges and 2 triangles. And so in the chat, please put the number of edges and triangles you get, or you can even annotate yourself the graph and draw where you get your points. So I get this point here, 9 edges, 2 triangles.
So we just draw any graph we want and tell
any graph you want on 7
Okay.
7 vertices, and count the number of edges and triangles and put the number in the chat, or just directly annotate on the graph. So Jan is getting 0, 0. Leanna got 3, 3. Leanna said no. Okay, so she'll get another one. So 6 and 1, 3 and 1. So single triangle, 4 and 1. Okay, that's good. We're getting lots of things. 8, 0. So which is here. Raise this one. Cool. What else do we have? 8, 0, 11, 4. So 11, 4 is here. Okay, so we could try to draw all graphs on 7 vertices if there were more of us. And we could see which points do we get, right? And so this brings us to the notion of a profile. So a profile is where I'm going to be counting either a number of certain substructures or a number of the densities of certain substructures, and then make vectors out of it. But so to talk about densities, I need to clarify what I mean. And I think, this is probably an audience that is pretty used to densities. So I'll go more quickly over densities than I would normally go. But there's different types of densities. So there's subgraph densities, which means that I'm looking at maps that are injected from the vertex set of my smaller graph to the vertex set of my bigger graph, and I just want to set edges to edges. Whereas when I look at induced densities, I want to make sure that non-edges go to non-edges as well. So for example, I couldn't have that this vertex here goes to this vertex, and this vertex goes to this vertex, and this vertex goes to this vertex. So this would not be an induced map, because then I have an edge between my heart and my question mark, and I want non-edges to go to non-edges. So that doesn't work as an induced map, whereas for my subgraph density, I would count that one. And so the one that I really care about is the homomorphism density. So the homomorphism density, I'm looking at all maps, not just injective maps. So two vertices can go to the same vertex from my smaller graph to my bigger graph. And all I want to make sure is that edges go to edges. So can anybody tell me how many maps there are from the vertex set of my smaller graph to the vertex set of my bigger graph? If I'm allowing all maps, not just injective maps, either in the chat or you can unmute. Daniel is saying 36. Who says more? Who says less? So you can think about how many vertices can each vertex go. So my first vertex can go to 4 vertices, and my second vertex can also go to 4 vertices because I don't need my maps to be injective. And then my last vertex can go also to 4 vertices. So in total, there's going to be 4 to the 3. And then I need to count which of these maps actually send edges to edges. So the 16 that I had for the graph density will still work, but then I get some extra ones. So for example, I could have heart is sent here, star is sent here, and question mark is sent also to the same place as a star, right? So that would be perfectly reasonable. Edges would still be sent to edges. And so because of that, so for every edge within G, there's going to be 2 ways of sending my path of length to, either like this or like this, let's say for this edge. So there's 10 additional maps than the 16 I already had there. So in total, I get 26 maps are homomorphisms out of the 64 total maps. So that's my homomorphism density. So homomorphism density is the density I'm going to care about. All these densities are related. So the subgraph density is just a Möbius transformation away from my induced densities. And asymptotically, if my target graph G, the number of vertices goes to infinity, while the difference between my subgraph density and my homomorphism density goes to 0. So asymptotically, they're the same. So we're going to talk about homomorphism density, but every result I'm going to tell you can be rephrased into these other densities. We just have to do a little bit of work there. But so homomorphism density is the one that we care about. So are there any questions about what homomorphism density is? All right. If not, then let's go back to the picture that we had started drawing together. So instead of looking at the number of triangles and edges, now I'm going to look at densities, right? And so the formal definition of a graph profile of some set of small graphs U, for me, is going to be the closure of all the vectors that record the densities of the smaller graphs within some graph G, right? So this is exactly what we were doing, but instead we were looking at the number of small graphs instead of the densities. So if we do it for edge and triangle, this is the picture that we get. So on the x-axis, I have my edge density. Here I have my triangle density. And so I'm taking the closure of all the vectors recording edge density and triangle density within some graph. And so here I'm using density really as homomorphism density. Otherwise, if I was looking at the other two types of densities, I would have to say for graph G where the number of vertices goes to infinity. But for homomorphism density, that's very nice. I can just do it for any graph. And so this is a really cool picture. So you might remember Mantel's theorem that says that if you have no triangles in the graph, then the maximum edge density is 1/2. Well, this is your x-axis, right? So Mantel's theorem is right there on the x-axis. Then you get like all of these scallopy little concave parts, and they keep going. I just, didn't draw all of them. And so here you have complete bipartite graphs with equal part, complete tripartite graphs with equal part, complete four-partite graphs with equal parts, and so on. And so these pictures are really cool, these graph profiles, and we know very little about them, right? So we know what they look like for edge and a complete graph. We know what they look like for edge and a path of length 2, and path of length 2 and a triangle. That's all. We don't know any graph profiles in 3 dimensions, right? So if I took, like, let's say, edge, triangle, and complete graph on 4 vertices, we have no idea what that looks like. Hatami and Nahin showed that, there's some complicated graph profile that they could take, that when they sliced it and projected it, then they got something that was almost nowhere differentiable. So we don't know how bad it gets. And certainly, edge and triangle is kind of the easiest case you could think of, and already it's kind of complicated, right? There's countably many of these little guys. Do we know non-triangle versus triangle? Jan, what do you mean by non-triangle? Like any graph that's, yeah, so that's kind of what I meant by like a path of length 2 and triangle. And I think you're right that we know, well, edge and triangle, yeah. So any 2 graphs on 3 vertices, we do know. But that's very little information. And so we would like to understand these graph profiles better in general. And so one way to try to understand them is to understand the inequalities that define it. So for example, here, this inequality, this curve, comes from the fact that the homomorphism density of an edge to the power 3 minus the homomorphism density of a triangle to the power 2, if I evaluate that within any graph G, I'm always to get at least 0. And so, okay, so this is what I'm going to be calling a graph density inequality. And so these are the kinds of things that we want to try to certify. So how can we try to certify them? Well, they look like polynomial inequalities. And well, in the normal world of polynomial rings, well, we have this technique called sums of squares, where we try to use sums of squares to certify the validity of some inequalities. So we can try to do the same thing here. But so before we do that, let's just talk a little bit about some results about certifying polynomial inequalities in the real world. So if I have a polynomial, a real polynomial, then I say that it's non-negative if whenever I evaluate it at any point in Rn, I get at least 0. Right? So for example, here I have this polynomial m of xy, and so whatever xy that I plug in, I never go below the xy plane. Right? So this is a non-negative polynomial. And I say that a polynomial is a sum of squares if I can write it as a sum of finitely many squares of polynomials, right? So the square of a polynomial is non-negative if I evaluate it on any point in Rn. So a sum of squares is going to be non-negative. So if I can write a polynomial as a sum of squares, then I definitely do know that it is non-negative. Right? So for example, if I show you this polynomial here, is it non-negative? Maybe if you spend a bit of time, you would say, yes, it is. But if I write it for you in this way, and then you just expand it out and see, oh yeah, these 2 guys are the same, you'll definitely say, yes, this is non-negative. I have a square plus another square plus another square. This is non-negative. So sums of squares form a nice way to certify non-negative polynomials. And so the first question you might wonder is, well, is every single non-negative polynomial a sum of squares? Can I always do this trick? And so we've known for a long time that no. So Hilbert in 1888 showed that not all non-negative polynomials are sums of squares. And he qualified it, characterized exactly which ones are. So after this result, Hilbert asked, well, maybe we're being too restrictive. Maybe, you know, asking for a sum of squares is too much. So what if we ask for a sum of squares of rational functions instead of a sum of squares of polynomials? So what if we allow to divide a polynomial by another polynomial there? Will this work? And so that was the 17th problem. And Artin in 1927 showed that yes, actually every non-negative polynomial can be written as a sum of squares of rational functions. So this was great. So it's a great theoretical result. In practice, this can be a bit hard to use. So whereas for sums of squares finding them, we have, you know, good systems to do that. For sums of squares of rational functions, we don't. And so one funny thing here that I want to point out is that Hilbert's proof was not constructive. So he said there exists non-negative polynomials that are not sums of squares. But it took until 1967 for Mutzkin, with the help of Olga Toski-Todd, to find an example of a polynomial that is non-negative, but that is not a sum of squares, and it's a polynomial that I graphed there. And so just to be clear, it is for sure a rational sum of squares, right? And so this is, you know, the proof of it. Well, not fully, but if I multiply m of xy by this sum of squares, then I get another sum of squares. So it can be written as a rational sum of squares. Okay, so these are like the traditional results in the world of real polynomials. So how do these transfer to the world of graph density inequalities? So I'm going to call a sum of squares of polynomials involving graph densities a graph sum of squares. And so the first result that we have is the equivalent result of Hilbert's result from 1888. So Hatami and Nahin in 2011 proved that not every non-negative graph polynomial can be written as a graph sum of squares. So that's not too surprising, right? It's what we expected. However, what was more surprising there is that they showed that it cannot even be done as a rational graph sum of squares. So this is the opposite of the Artin result. So this was a first surprise. So seeing that, you might wonder, well, are sums of squares even good, a good tool for the world of polynomials involving graph densities? And well, from Lovas-Segedie and Nesser-Tom, we do know that every non-negative graph polynomial plus any epsilon greater than 0 can be written as a graph sum of squares. So if you're willing to go approximately, then you will be fine. You'll be able to do it. And so just like in the case of the Hilbert result, well, this proof was a bit more constructive than Hilbert's proof, but certainly you couldn't come up with any example that would ever show up in extremal combinatorics that you would ever want to show as being true. So people were wondering, well, maybe sums of squares are good for anything that's natural, right? And so in 2018, with my collaborators, we showed that no, actually, there are very simple inequalities involving graph densities that are non-negative, but that cannot be written as graph sums of squares. And so here's the smallest example that we found. So if you take the homomorphism density of a path of length 3 minus the homomorphism density of 3 disjoint edges, within any graph, it's been known for quite a while that this is always greater or equal to 0, but actually cannot be written as a graph sum of squares. And so a bit later, we showed that it cannot be written as a rational graph sum of squares. And so we showed this for bigger classes of graphs too. This inequality is the smallest one, and it's part of these inequalities called the Blake-Leroy inequalities that already existed before Blake-Leroy, actually. And they're, you know, an example also of Sinner-Coase conjecture, which I'll say a few words more about later. So for the rest of the talk, I want to tell you a little bit about how we did that. So for the graph sum of squares part, what we did is that we characterized exactly which homogeneous graph polynomials of degree 3, so involving only graphs with 3 edges, can be written as graph sums of squares. And this guy is not one of them. And for the rational graph sum of squares part, we studied the tropicalization of the set of points that sums of squares accepted. And so tropicalization ended up being an interesting object in its own right. So I'll tell you a little bit about that too. But so before I go further, are there any questions about sums of squares, either in the real world or in the graph world, or about anything else? All right, so I will keep going, but please don't hesitate to stop me at any point. So what tools do we need for graph sums of squares? So the first thing that we need is to understand maps that have some partially labeled graphs in them. So you would think that, okay, the inequalities I'm trying to certify only involve unlabeled graphs. So why am I bringing in partially labeled graphs within my sums of squares? The reason comes from representation theory, and I'll just say a quick word about it. The point is that if I were only allowing to take squares of unlabeled graphs, of expressions containing unlabeled graphs, it's as though I would only be using the trivial representation. So I would not be using the full decomposition. And so I would not have the full power of sums of squares in that way. So I do need to consider partially labeled graphs. So what does it mean to look at homomorphism of some graphs within some other graph where I have some labels within my first graph? I'm really thinking of my second graph to be unlabeled. I only put numbers there because what the map does, what the numbers in my first graph means that I know exactly where those vertices are going. So really all I'm saying is that this vertex is going here and this vertex is going here. So my heart goes to my heart, my star goes to my star, and then any unlabeled vertices can go anywhere. So here there's 6 vertices that it can go to, right? Again, I'm considering maps that are not necessarily injective. And so there's 6 places it can go to. And so which one sends edges to edges? Well, I can send my unlabeled vertex either here, here, or here, so that edges are sent to edges. Nowhere else will it work, right? So if I send it here, for example, if I send it to the heart, then there would be no edge between edge and heart, and there needs to be. And same thing if I send it here or here, again, there would be no edges between my heart and my check mark. So that wouldn't work. So this homomorphism density of this partially labeled graph within some target graph G, which I put here, is 3, 6. Does that make sense? Any questions about partially labeled graphs? So given that my sums of squares, given that the expressions I'm trying to certify at the end are completely unlabeled, certainly I need to know how to unlabel my my sums of squares. And so my unlabeling will come from symmetrizing. So I'll denote that by taking double brackets. And so all I'm doing here really is that I'm summing and normalizing. I'm looking at all of the places that vertices 1 and 2 could be sent to. So effectively, I am relabeling, this unlabeled graph G that I have as a target graph. So instead of saying that 1 and 2 go to 1 and 2, maybe I send them here instead. And then I'm considering every single way of putting my heart and my star within this bigger graph. So in the end, once I do this and I normalize, all I'm really doing is finding the homomorphism density of a path of length 2 within my target graph G. And so just to be very clear, this is a sum, really. I really want to think about it as a sum because I want a sum of squares. So the final tool that we need to do sums of squares is to know how multiplication happens, right? I'm going to square, so I'm going to have to know how multiplying works. And so here it's very nice in the case of homomorphism densities. All multiplication is gluing along vertices that have the same labels. If any edges become double, I just keep one copy. So if I multiply this first guy with this second guy, well, I just get their glued version together. And, you know, the two vertices that are unlabeled within my second guy, well, they can go to the same place or not, right? Because I'm looking again at homomorphism densities. If I was looking at subgraph densities, this would only hold if I looked at target graphs where the number of vertices goes to infinity. And here, if I looked at induced densities, because of the Möbius transformation, it would be a bit more complicated to write. So homomorphism densities here allows us to have this very clean picture for multiplication. All right, so now I have all the tools that I need to be able to think about a graph sum of squares. So let's do an example. Let's try to show that the homomorphism density of a path of length 2 minus the homomorphism density of two disjoint edges is always non-negative. So whatever graph that I evaluate this in, I'll always get at least 0. So here is the sum of squares proof. Normally I would just write this. I'm writing the rest just to expand it out to really show you that it works. Again, double brackets means unlabeling, and it's really just a normalized sum. So this is really a sum of squares properly. So let's see that it works. So I square, that means that I take the square of the first term minus 2 times the cross product plus the square of the second term. Okay, so now I do multiplication. Anything that has the same label gets glued together. So I get a path of length 2 with the middle vertex labeled 1. Here there's no vertices in common, so I just get this guy again. And then here the label 2 gets glued together, and I get a path of length 2 with the middle vertex labeled 2. Now I sum and normalize, and all that does is unlabel. So I get 2 times the path of length 2 minus 2 times 2 disjoint edges. I take 1/2 of that, and this gives me exactly a path of length 2 minus 2 disjoint edges. And so this tells me that, yes, this is non-negative. This is my sum of squares proof for it. Any questions about how we write sums of squares? All right, so here is one weakness that we found for graph sum of the squares, and there are more, but this is the only one we know. So consider a homogeneous non-negative graph polynomial. So a non-negative graph polynomial where all the graphs involved have the same number of edges, and there's d edges, that's why we say of degree d. And so let's say that I look at a polynomial that can be written as a graph sum of squares. Then I know that in that case, there does exist a very, very specific way of writing my sum of squares, where any two monomials in any given square multiply to have degree d. So maybe I just draw a little example. So for example, if I could have this guy minus this guy within the same square, because if I take the square of this guy, okay, I get a star. Their dot product is going to be a path of length 3 plus, again, a star for the square of the second term. So all of these terms have 3 edges. So that's allowable. Whereas if I had say this would not work. So if I squared this and symmetrized it, I would get, okay, a 3 star again, minus actually the cross product is a 3 star as well, and then plus a path of length 2. So I would get things of degree 3, 3, and 2. So that's not allowable. So what this is saying is that within my squares, so if there is a sum of squares, I know that I'm going to write it in this very constricted way where things don't cancel out, where everything within, either my squares or my cross products will always give me the same number of edges within my graph. And so for that, it's very easy to see that all that means is that your partially labeled graphs must be such that they have exactly the same fully labeled edges. And so once you know this, then it's pretty easy to write out all of the graph sums of squares of a particular degree.
Danielle,
so yes, Liana, please.
Can someone ask a question? What's the idea behind the proof here? Danielle Fish was asking.
Yeah, that's a good question, Daniela. So the proof, the very big thing here is to show that things don't cancel out. And so we just created a functional that shows that this will not work out. But so that the canceling out not being possible between things of bigger degree is really what is so important there. And yeah, we create a functional to show that this doesn't work out.
And sorry, I don't think I understand the statement yet. So it's essentially saying that the individual terms have d-half edges, except it's a bit more complicated because something is happening in the labeled part.
Yes.
But
yes,
are you saying that the labeled part has to be the same, or can you can you make it more precise, or can you say more?
Yeah, so the labeled part, let's say, within the labeled part, I want to think about fully labeled edges. So here, these would be my 2 fully labeled edges. And so I can assume that within each square, all of the graphs there will have exactly the same fully labeled edges. So for example, I could also have, and then the total number of edges should be the same as well. So I could have, I'll use the same color. So I could have 1, 2. Oh, I have a line, that's why this is not working well. And then 1, 2, 3, 4. So these 2 guys, for example, have exactly the same labeled edges and they have the same number of edges. So this would work. Or I could have 1, 2, 3, 4, and then an additional edge coming out of 3. That would be fine. Does that make more sense, Jan?
Yeah, thanks. Mm-hmm.
Okay, great. So yeah, so this is saying really that there's a very restricted type of sums of squares that we can look at. And once we do that, then it comes out pretty easily, for example, for graphs of degree 3. So there's not many graphs with 3 edges. These are the guys that have 3 edges. And now we can think about, okay, well, I cannot get more than 3 edges. So there's not many smaller graphs that when squared will give me at most 3 edges. I can write all of them with the possible partial labels. And then I can only use the ones that have the same fully labeled edges. And then I get that this is the shape of any sum of squares. So I have to have that all of my A through G's are non-negative and my M1, M2, M2, M3 need to be a PSD matrix. And so now you can just say, okay, well, if I want to know about a particular inequality, so if I want this to be -1 and this to be 1, so I have the Blake-Leroy inequality, can this happen? Can I have A through G be greater or equal to 0 and this matrix be PSD so that I have 1 and -1 here? And then it's an easy no. So this theorem is actually a bit stronger than that. So here I wrote it as homogeneous non-negative graph polynomial, but that's actually true for the lowest degree part of your polynomial. And that's kind of why the Netzer-Thom-Lovasegedi theorem works so well, right? Because when you add a plus epsilon, then your lowest degree part becomes a part of degree 0. So you're making it, you're removing this hardness of the lowest degree part having this restriction on how the squares for that part need to look. So using this theorem, we can show that the homomorphism density of path of length 3 minus 3 disjoint edges cannot be a sum of squares, even if you add more paths of length 3. So even if you make it more non-negative, it still won't become a sum of squares. If I multiply by a sum of squares 1 plus g, right? So this was a question of Lovas, which was starting to go in the direction of rational sums of squares, then this will not work either because the lowest degree part will still be the same. So by the stronger version of the theorem, that still won't work. You can think about Siderenko's conjecture, which states that for any bipartite graph H, the homomorphism density of H minus the number of edges and H copies of an edge is greater or equal to 0. Well, you know, so this is a homogeneous polynomial. So we know that the previous theorem will help there. And so there we have this concept of a trivial square. And so if the only way that I can write H as a square is by fully labeling H and squaring it, if there's no other partial labeling that will work, then there will not be a sum of squares proof. And for example, for the smallest open case of Siderenko's conjecture, that is the case. With Amanda Rettlich, we have been thinking about different results that are known from Siderenko's conjectures. Many of them involve things that are not trivial squares. And so, you know, like the hard cases most likely are the cases when graphs H are trivial squares. All right, so this is what I wanted to say about sums of squares. And now for the rest of the talk, I'd like to switch over to tropicalization, which will bring us back to rational sums of squares. But are there any questions about sums of squares before we move forward? All right, so let me tell you a little bit about tropicalization. So we saw that this idea of a graph profile, right, like edge versus triangle, was already very complicated. And so in general, we don't know how complicated it is. So it would be good to know how to simplify it. And so tropicalization is exactly what it does, is it simplifies it greatly. So what does tropicalization does? So I have this log operation, which I take any point V. And what I'm going to do is that I'm going to take the log of each component. And so I can take the log in whatever base, right? So this is really just a change of bases here. And so the logarithmic set, or the tropicalization of my graph profile, is I'm going to take the limit as k goes to 0 of the log in base 1 over k of every point in my graph profile. And so this sounds, you know, if you've never done any tropical stuff, this might sound very weird. So the idea here is that you go from your normal polynomial ring with addition and multiplication, and you move over to another ring where you have, you take the maximum and you add instead. So you move from addition and multiplication to taking the max and adding. So that simplifies things. And so in particular, you know, it takes, if you have a binomial originally, once you do this operation, you're going to get a linear inequality. And so the tropicalization of my graph profile turns out to be much simpler because of that. So it turns out that we can show that the tropicalization of the graph profile is just a closed cone, right? So we had this very complicated picture already for edge and triangle. And so here we're saying no matter what your set U is, your tropicalization is always going to be a closed cone, and it's going to be determined by the linear inequalities corresponding to the binomial inequalities valid on graph profiles.
So sorry, Annie, so
yes.
Understand, and now this graph G, that I should think of it as possibly unbounded graph one, right? So you need to have, if you were originally constrained to the interval 0, 1, then this tropicalization would make everything trivial, right? Or
what do you mean?
Well, okay, so now.
So maybe I show this picture. Maybe this picture helps a bit.
Okay, then yes, then I will shut up and listen.
Well, no, I do want to hear your question, but maybe this will make it clearer, and then we can revisit your question, Jan. So, for example, this was the example that we started with, right? And so I am between 0 and 1 everywhere because I'm looking at densities. And so by doing this, I do know that I'm going to be in the negative orthant. And so, for example, this curve that we had before was a binomial. It was the edge density cubed minus the triangle density squared was greater or equal to 0. So once I take the log of this, I just get 3 times the log of my edge density minus 2 times the log of my triangle density. So I just get this nice linear constraint. I lose all of these details. All I'm keeping are the binomial inequalities. And there's plenty of interesting things about graph profiles that are not binomials, right? There's plenty of inequalities that are not binomials. And I'm losing all of those, but I'm keeping the binomials. And I think that's still pretty interesting because, most of you are in extremal combinatorics. A lot of problem in extremal combinatorics are about binomials, right? So you are keeping something not trivial, something that we do care about, and yet you get a cone instead of something very complicated. Jan, let's go back to your question. Did this clarify anything?
Yeah, I'm not entirely sure what. So you are. Is it that you are capturing just things close to 0, 0?
Yes, in a sense, completely, because of the tensoring trick. Really, what I'm doing is understanding the neighborhood of 0, 0. You're completely right about that. That's a very good point. Any more questions about what tropicalization is doing? Yeah, and that's amazing, right? You're only keeping what's happening close to 0, 0, but that tells you everything you need to know about pure binomials. And so it turns out to be simpler, right? So I told you that for graph profiles, we don't know any of them where you have more than 2 graphs. And even for 2 graphs, we only know a few. But for the tropicalization, for example, we can do some infinite profiles. So give me any set of complete graphs, and then I will be able to tell you what a tropicalization is. And it's actually very easy to characterize. So there's Kruskal-Katona's theorem that says that the homomorphism density of a complete graph on p vertices to the power q minus the homomorphism density of a complete graph on q vertices to the power p is greater or equal to 0 whenever p is smaller than q. Those are known to be valid binomial inequalities, right? So they're going to be valid binomial inequalities for my graph profile. And certainly I also know that the homomorphism density of an edge is at most 1. And so it turns out that these are all the inequalities that I need to describe the tropicalization of my graph profile. And so the way to show that this holds, certainly I know that my graph profile, the tropicalization of my graph profile will be within that, right? All these inequalities are true inequalities, they need to hold. But then I just need to show that the extreme rays of the cone that I get from these inequalities are actually realizable. And so these are the extreme rays that I get. And it's easy to show that they are realizable. And so what this is really saying is that there are no other interesting binomial inequalities involving only complete graphs except for Kruskal-Katona. Any other binomial inequalities can be derived from the Kruskal-Katona inequalities and the fact that a single edge has density at most 1. And so we can do the same for complete hypergraphs and for stars and hyperstars. You know, you can take as many as you want, and you can fully characterize their tropicalization. So that's pretty fun. But you might say, well, we already know Kruskal-Katona, so sure, it's great to know that there's nothing else interesting going on there, but can you show anything new? And so, well, we almost showed something new. So there was this conjecture by Erdős-Szymanowicz that said that if you take the homomorphism density of a path of length t, so with t edges to the power s, well, that's greater or equal to the homomorphism density of a path with s edges to the power t for s and t odd, t greater or equal to s. And so by looking at the tropicalization of all paths, we were able to show that this is true. We thought we were the first, but then we realized that Mert Saglam had already proven it 2 years prior with completely different techniques, using heat configurations and measuring different things there. But so looking at the tropicalization, we were able to do that. And so we should be putting on the archive pretty soon a paper that gives a full description of the tropicalization in this case. And so we actually do give a generalized version of Erdős-Szymanowicz type inequalities, as well as all inequalities that are needed there. And so,
sorry, can you go?
Yes, Liana, please.
Just for a second. Can you maybe explain what this means? So in terms of Sidorenko's conjecture, what would this mean?
Oh, well, this is not related to Sidorenko's conjecture directly, right? This is only about paths. So Sidorenko's conjecture is a bipartite graph and edge to the power of the number of edges in the first graph, whereas this is some inequality between paths. So just a different inequality that people cared about. I don't know if it might have some implication on Sidorenko.
If I were to think of, like, is there any intuition what it means in terms of just if I thought about graph densities, known.
So is there intuition for why this holds?
Mm.
Yeah, I mean, so part of the proof technique that we had to rely on was work that was done by Kopati and Hausmann that shows that there is a linear program to kind of calculate this exponent t in certain cases. And so in this case, it gives t. And so it's kind of finding ways of sending paths within each other. I would say, yeah, it took me a really long time to build my intuition there. Yeah, it's not all that, but yeah, there is something about, yeah, how do you send, so how do you send your path of length t within your path of length s, so that you cover all vertices and edges within your path of length s exactly t times, is kind of the idea. But yeah, it's yeah, the intuition is important, and yet unfortunately hard to describe in this moment. So very quickly, so how does this all relate to rational sums of squares? Well, so okay, we have our graph profile, and so now we could think about looking at everything that is accepted by sums of squares, right? So sums of squares won't be able to find all the inequalities that define our graph profile in general, but we could let SD be, okay, I'm allowing for graph sums of squares involving up to d edges. What points am I obtaining? So I'm going to get all of the graph profile plus some stuff. So this is really all this is saying. And so I could even relax my SOS profile to say, instead of having that all those special moment matrices that I don't want to get into, you normally hear that means that all principal minors need to be non-negative. I could relax this to say just all 2 by 2 minors. So I get these different bodies. So I have my graph profile, then, which sits within all of the points that are accepted by my sums of squares of degree D. And then I relax that even further to having just the 2 by 2 principal minors to be non-negative. And so it turns out that when I tropicalize these guys, well, the tropicalization of my sums of squares profile is just the log of my 2 by 2 relaxation. So that means that my tropicalization of my sums of squares profile is a polyhedral rational cone that is fully determined by 2 by 2 principal minors of my moment matrix. So I can fully describe it. Whereas for the graph profile, sure, I simplified, I got a cone once I tropicalized it, but I didn't know anything about that cone, right? I mean, I knew it was closed and convex, but not more than that. I didn't know how to fully describe it in general. Whereas here, for the tropicalization of the sums of squares profile, I know exactly what it is. And so this allows us to show that certain polynomials cannot be written as rational sums of squares. So if I have some binomial that is non-negative, so some binomial A with these powers for my graphs, so I can take the log of that, right? And the log of that is going to give me such an inequality. So I want to show that this inequality is not valid on the log of my 2 by 2 relaxation. And if I'm able to do that, then that means that there exists a point within my sum of the squares profile that is on the other side of A. So such that A applied to V is smaller than 0. And so that means that A cannot be a rational graph sum of squares, because otherwise that would mean that there are some graph sums of squares B and C where V, when I evaluate it on V, that's greater or equal to 0, because I do know that V is an SD. It's in my sum of squares profile. It's what my sum of squares accept. So B applied to V has to be greater or equal to 0. And same thing for C. So it gets something smaller than 0 times something's greater or equal to 0 is equal to something greater or equal to 0. Does not work. So that's how we use tropicalization to show that rational sums of squares do not always work. And so then we can give specific example of what these graphs are, where we can find that it's not a valid inequality. So what are the takeaways? The first takeaway is that homogeneity is a weakness for both sums of squares and rational sums of squares. It also shows us that sums of squares might not be the best tool for homogeneous problems in extremal graph theory, such as Siderenko's conjecture. It won't be able to prove everything, right? And just to be very clear, sums of squares is the same thing as the Cauchy-Schwarz method, right? So you might be more familiar with that name. They're equivalent. So it's not the only thing. You cannot use only that to prove Siderenko's conjecture. But then, throughout all of this, we found this very interesting object, the tropicalization of the graph profile, which, gives you a lot of information about binomial inequalities, which we do care about in extremal graph theory. And so we want to understand this tropicalization of graph profiles in general better. So every example that we have found, which of course are the simpler examples, are all rational polyhedral cones. Is that true in general? Will that always be true? We don't know. And so this would have some effect on the decidability of binomials involving densities. So that would be very interesting. We still don't know that rational sums of squares are actually stronger than sums of squares. So it would be nice to find an example of a non-negative graph polynomial that is not a sum of squares, but that is a rational sum of squares. And then when sums of squares fail, we need something else. So there's these newer certificates called sums of non-negative circuits. And so I'd like to study them to see how they fare for non-negative graph polynomials, because maybe they do better, especially since they're related to relative entropy, which is such an important technique within extremal graph theory. And I will stop here. Thank you.
Thanks a lot, Annie, for a very approachable talk. It was great. Let's unmute ourselves and thank you, Annie, by giving the round. So feel free to ask questions. And, Henry, you had a question. Do you want to?
Yeah, so Henry asked for conjectures or open problem like surveys. I mean, actually, I would love to know that. So I think, that's more of a question for me to you is, yeah, what are some conjectures that you know of in extremal graph theory that really end up being binomials? Because I know of some, but I am not the most deeply connected person to the extremal graph theory community. So if you know of any binomial inequalities that you think are interesting, I would love to hear about those.
So I have a question or maybe a suggestion. How things work for other structures than graphs. So two structures which come to my mind are permutations, where the natural notion of density is maybe a bit more like induced density. I'm not quite sure. And then some patterns on like basically functions on abelian groups, right? So things which you have to study when you want to understand, say, Semeradis theorem.
Yeah, this is a great comment, Jan. So we actually did look at a few other structures besides graphs and looking at the tropicalization. So for example, for matroids and simplicial complexes, in both cases, the tropicalization is always a rational polyhedral cone. We can show that. We haven't done permutations. We've thought about it, but we haven't done it yet. And then, yeah, abelian groups we hadn't thought about. That's a great idea. But yeah, you can play the same game in different places where you're counting different things and tropicalize and get something interesting. Yeah, there needs to be certain things. So two things that end up being very important here is that you have the Hadamard property. So the product of two vertices is going to be within the profile. So anything that has the Hadamard property is going to be really well behaved in the tropicalization world. And then in the case of graph profiles, one thing that makes it even nicer and that we are using is the fact that it is max closed. And so when things are max closed, what's going to happen is that the only binomials that can be interesting, that can be extremal in a way, are going to be binomials that have only one graph on the smaller side. And so that restricts a lot what you can have as inequalities. Then Henry asked, does matroid have some clues to study using this topics? What do you mean, Henry? What did you mean, Henry?
I guess would be that he means, is there applications of this theory in matroid theory? That's what he means.
Yeah, we did not learn anything new. So the tropicalization was simple there. So I don't think that it can help. You just had like non-concativity inequalities and things like that. So you didn't get anything new. It was a bit like, in a certain way, not so far away from the case of, all complete graphs where, okay, all you need are Kruskal-Katona inequalities, which were already known. So just telling you, okay, you don't need to ever think harder about binomial inequalities for matroids. The only interesting ones are already known.
So another question I have is, you were talking about graph densities, but there is this notion of graphon, and then this notion of density is just an integral, which then makes sense for any, say, symmetric infinity function. So you don't need to be upper bounded by 1, and you don't need to be non-negative. Would that, if you switch to this, signed world, would anything change?
As I understand it, no. So I am not the most well-versed person in graphons. As I understand it, so any sum of squares proof can be transformed to an integral proof and vice versa. But yeah, I'm definitely not the most, I should know more about graphons than I do.
Yeah, but if basically your only tool was squaring densities, and it's like squaring polynomials, you don't need to know whether the value of your variable is positive or negative. It always squares to something non-negative. So then it doesn't make a difference. So
yeah, so if it's basically just using Cauchy-Schwarz within your integrals.
okay.
Excuse me.
And so, of course, like some people will add tricks where they will, add roots in places that we would never add roots. And so that does make it more powerful. And so we can actually show that if you allow to take roots for your densities within your squares, then you can certify anything. But then how to do that in a computationally efficient way is not trivial. We don't know how to do it.
Can you hear me?
Yes, a little bit.
Okay. I mean, matroid, we have two collection of set, okay, about membership and something else. Okay, we have a set, a base set, and on it we have a collection of set. We have three principles or something like that. But I mean, there have some connection between SOS, scale of SOS, squares of some element between matroid and this. You said about that this is simple ideas and approach. Okay, about can you hear me? Okay.
I'm hearing so. We're kind of cutting
I don't know
a bit.
the concept. I mean, some conjectures you said is whole, is done. Okay, some conjectures about these topics. But I mean, graph is not this topic. The slides, I mean, the elementary slide. Yes, in conjectures whole. Now, some we have do you have some conjectures is open in this open to dispute? I mean, for working in long term, for example, not is about the short term or something. I don't know. There are different levels for working, but I mean, it's so nice, something like that. Because I'm unfamiliar with these topics completely. It's obvious. But I want to enter to these topics. So I find some ways, some avenues, some I don't know road direction that I don't mean goes to be conclude or as some I don't know ideas for working, but I jump another topic and got something else. Some ideas we have I don't know interface, deep interface, deep rooted in these topics. For example, have edges and triangles. We look at the graph and how many counting about these ideas, but this choice, this I don't know, this proportion of mind for getting some points, choosing some element 2 or 3, something like that. I don't know. They have a lot of ideas about the graph theory, a lot of problems. Something else, I don't know.
Yeah.
To illustrate the clarification for that, but I'm trying on it. But I don't. I mean some problems, or I don't know. This is some ideas to enter, not the main case of a problem. I work on it. Some nice ideas to be so close to each other, for working closer and closer to. I don't know. They have a uncertainty. I mean something not obvious or goes very fast. We have a lot of work to that. These topics, I don't know, jumping another branch goes between a medium and go back to that case. That's we have a report for this. I love that your stuff. We have recorded for that. Actually, I mean, on first time using your links and the platform for communication and these types of conference. But I mean, I try to say something. I don't know.
Yeah, I mean,
something else.
Yeah, no, these are good questions. I mean, I think, yeah, like, so obviously there's conjectures, like one could try to go straight for the conjectures that people in extremal graph theory care about, and then that will most likely be very hard in most cases. In a certain way, when we looked at all paths, that's something that we were trying to think about, was something, okay, that was maybe going to be feasible. I think cycles of any length should be feasible as well, that we should be able to say something there. But then, you know, the interdisciplinary part that you're saying. So for example, Mohit Singh, who had proven it with different techniques, is in TCS, right? He's in theoretical computer science. And so he cares about complexity, communication complexity. And so they have inequalities coming up there that they're interested in, which I've been meaning to read up on those. And so they might be a good place to start because they haven't been using these techniques at all. And so seeing what inequalities they care about in that community might give good ideas for conjectures to try to solve that haven't been tried using these techniques.
Thank you.
Okay, let's thank Ani for once again for also answering all our questions. Many thanks, Ani.
You're welcome. Thanks everybody for coming.